Okay, let's look at dataset number 4. Let's plot this first. And we immediately notice that this dataset has not only values that are equal to 1 and equal to 0, but also values in between 0 and 1. So if you look at Y-list, looks like there's one value that's equal to 0, a couple of values equal to 1, and we can say Y-list 0, there's one value that's equal to 0, and a couple of values equal to 1. Okay, and we can try to run the old logistic loss with binary loss function, right? So this binary loss function only really works for when y-list is either 1 or either 0, and really we're just summing over the data points that are equal to 1 or equal to 0. And if we just use this function, we would just be completely ignoring all the data points where y is between 0 and 1. So you shouldn't even be using this logistic class function with binary, because it really just considers only 0 and 1. Let's see what it looks like anyway. Just looks like a mess, right? Because it's just trying to do something, I guess. Yeah. It's ignored most of the data. It just has 3 data points and it's fitting 2 coefficients. And yeah. Okay. So what we really want to do is there's this other function that is provided here, which is logistic loss function continuous. Let me do that. So this is what we want to use. And this function actually does 3 different versions of the loss function. If the output is equal to 1, then it essentially evaluates this expression corresponding to the binary case. If the output is equal to 0, it evaluates this expression corresponding to the binary case. So it's sort of done in this manner. P1 is all the indices where y is equal to 1, P2 is all the indices where y equals 0, and P3 is all the indices that are neither 0 or not 1. Hopefully they're between 0 and 1. If it's outside of 0 and 1, there may be problems, but okay. In any case, so L of P1 is minus log the logistic function of z at P1, okay? So basically we evaluate the pieces of the total loss function and then use that when when y equals 0 and y equals 1, and when y is neither equal to 0 or 1, we have this more complicated looking loss function expression, which we went over in the notes very briefly. And this is just a direct copy of that expression. And this works when the value of the output is between 0 and 1. So we sort of separately compute these loss functions for each data point, depending on whether it's 1 or 0 or between 0 and 1, and then take the mean of all the losses. Okay. So that's what we're going to use. And then there is this additional line. Let me just comment that out. There's an if-then statement here, which I'm going to ignore for a moment. And let me just run this thing and we'll see what we get. Okay, we get some error. Okay, it says function evaluates to inf check function evaluation and make it smooth, error in line search, blah blah blah. Actually, this has to do with the error command that we ourselves stuck in to this function evaluation. So, and it says like the function evaluation is infinity. Basically, it's claiming that for the initial guess for B, this B, basically this B, the value of L is actually infinity. It's like I say if is inf of L, then say this error out like this. And that's what happened. Now, why did that happen? Um, the clue actually lies here. It's kind of a very subtle point. Let me run this and plot this again. Okay, so this is y as the function of x. And notice that x is in the many thousands. Okay, x is in the many thousands. And then for the logistic function, the sigmoid function, we are trying to evaluate a function that looks like 1 over 1 plus e power minus b naught plus b1 x or something like that. So if the thing in the power, for instance, was a very large number, like in the few thousands, what you might get is like a very large number like e power 1000, and you might get infinity like that, right? So or something, right? So you can imagine, or that's one case. I guess there actually you'll have 1 over infinity, which is 0, but there are all these logs and things like that that might, if the numbers are too large or too weird, let's say, you might get these weird singularities or infinities being evaluated. You can try to localize the exact reason for this infinity. I'll leave that as an exercise, perhaps. Um, but what we're going to do is uncommon this piece. Uncommon this piece. What this does is run this, and here the x's range in the many thousands. What I'm doing here is reassigning x. I'm subtracting out the mean from x and then dividing by the range of x, right? So subtract out the mean so that it's centered around 0. And then I'm going to divide by the range, which is about a couple of thousand. And what that will give us, let me run this thing, is what's called a normalized x list, which basically the range is like minus 0.5 to zero point 0.5, right? Um, what this ensures is that there are no like powers of very large numbers and so on. And all the numbers that we're dealing with are relatively small, 0 to 1. When you have very large numbers, you get weird numerical artifacts having to do with raising 10 power 1000 and so on, which are just such large numbers that you get sometimes meaningless results with numerical computation. Okay, so this is called a normalization step, or sometimes called a standardization step, which is very useful. So one way to do this is divide by the range, which is maximum minus minimum, which is sometimes called min-max normalization. Another way is called z normalization or z standardization, which is dividing by the standard deviation of x list, which we've already seen, basically the z-score. And that also gives us values that are relatively small along the x-axis. Okay, so all we have done is normalize the inputs from many thousands to in a reasonable range between, I don't know, -2 and +2 or something. Let me run this whole thing again. And notice that we get this really nice smooth fit. It had no problem, there were no infinities and so on. Okay, so that's it. We just minimized the logistic loss function to fit this data, except we used this more complex function that allows for the outputs to be between 0 and 1 in the data. And we used the exact same procedure where we used fminunc. And that's it.